Let's take a look at number 1. We have an 8 Newton weight and we're pulling on it with a force of 6 newtons. So the only force that's acting on it, or the only net force, is the force to the right. So that would just be 6 newtons to the right. And therefore, in order to put it into equilibrium, you would have to provide an equal and opposite force. So that would mean a 6 Newton force to the left. So I realized that the way this question was worded was a little bit ambiguous, so I apologize for the confusion, but it's really more of a conceptual question. Let's take a look at number 2. We're given 2 angled forces that are pulling on a ring, and we need to find the net force. Well, anytime you have an angled vector, the very first thing you do is separate it into its components. We can use a cosine function to find the x component, and we can use a sine function to find the y component. Let's go ahead and do that for the other vector as well. What you'll notice here is that we have the same valued vector, and we have 60 degrees and 30 degrees, which are complementary angles. So that means that the values that you get when you use sine and cosine are really going to be the same thing. They're just going to be swapped. Anyway, let's add up all of our x components. That's the 53.7 plus the 31. And then let's add up all of our y components. That's the 31 plus the 53.7. So it turns out it's the same thing in the x and y direction because the angles are complementary and the value of the angled vectors is the same. So you already know it's going to be 45 degrees. Let's use the Pythagorean theorem to find the resultant. So the way you would word this answer is 120 newtons at 45 degrees. And number 3, again we have some angled vectors. So before I do anything else, I'm going to separate them into their components. I didn't show the work for the x component because it's a 45 degree angle, so I know it's going to be the same as the y component. Same thing for this one. I'll use my cosine function to find the x component, and I know it's going to be the same for y because it's a 45 degree angle. So to find the net force, we need to add up all of our x's, and then we add up all of our y's, and that's going to be the net force. But the question is, how do we put it in equilibrium? Equilibrium means everything's canceled out. So equilibrium is going to be the exact opposite. 8.4 newtons to the left and 59.4 newtons up would cancel it out. So what would that force be? You got to use the Pythagorean theorem to figure out what the actual force would be, 60 newtons. And then you can use your inverse trig functions to figure out what the angle would be. So the way you would word this is 82 degrees west of north. Alternatively, you can just find the counterclockwise angle starting from 0 degrees. And number 4, we're throwing a stone off of a cliff. The initial velocity is only in the x direction. We know the height. So let's write down what we know in the x and y directions. We know the velocity initial in the y direction is 0. Acceleration is gravity. And we know the distance. So we have enough information to find the time. We can use this kinematics equation here to find the time. I need to make my distance negative here because it's down. Let me pause the video for a minute and add a little negative here. It should be negative 78.4 so that your signs work out correctly. Okay? So now that we've found the time, we can put that over there in our x section because it's the same for both directions. So now we can find the distance in the x direction because we have the velocity and the time.
Angelo Stanich, please report to Miss Janik's room. Angelo Stanich to Miss Janik's room.
Okay, now we need to find the final velocity in the y direction. We know the initial velocity, we know the acceleration, we know time now too. So we can use this kinematics equation to find the final velocity in the y direction. It's negative, but that makes sense because it's going down. So now I have my final x velocity, which is the same as the initial, 5. I have my final y velocity, 39.2. So you can find the resultant if you wanted to. It doesn't look like it's required for question number 4, but if you wanted to, you could use the Pythagorean theorem to find the actual velocity vector when it hits the ground, and you could even find the angle too, using an inverse trig function. And number 5, we do not know what the initial velocity is, but we do know the distance in the x and y direction. Let's plug in what we know. Looks like I have enough information in the y direction to find the time. I can use this equation right here. Looks like I forgot my negative again. Let me put that in right now. If the distance is in the negative direction, then you got to make it negative. Otherwise, you'll end up with a funny answer.
Coach Fry, could you please call the front office? Coach Fry, call the front office. Thank you.
Okay, so now that I have time, I can solve for velocity in the x direction because I know the distance. And it looks like that's all we need to do for this one. In number 6, I'm given an angled vector. The first thing I'm going to do is separate it into its x component using the cosine function, and also into the y component using the sine function. Let's summarize what we know about the x direction and what we know about the y direction. I can find the time here by using the half of the trip. I can use half the trip to find half of the time, because halfway through my trip, my velocity final in the y direction is going to be 0. So I can find half the time in the y direction, 1.38 seconds, and then just multiply by 2 to get the total time. Remember that the time is the same in the x and y directions, so I'm going to go ahead and put this in on both of my banks. Let's find next. Let's find the maximum height next. We can use the VF squared equation in the y direction for this one. I know the initial velocity. The final velocity is going to be 0 at its maximum height because that's at the very top of the trajectory. And at the very top of the trajectory, the velocity in the y direction is always 0. Now I have my maximum height. Next up, we need to find the range. The range is just a fancy word for the distance in the x direction. Well, I know the velocity in the x direction. I know the time in the x direction, so I can find the distance. In number 7, we do not know what the velocity initial is. We do know what the distance is in the y direction and in the x direction. Let's summarize what we know. I can use this equation right here in the y direction to solve for the time. Don't forget to make that distance negative because you're going down. And then you can find the time in the y direction, which is also the same as the time in the x direction. So now I can find the velocity in the x direction because I know the distance and the time. Number 8, I'm provided with an angled vector. So the very first thing I'm going to do is separate it into its x component and its y component. I'm not going to show you the trig anymore. I think we've done enough of that at this point. Let's summarize what we know. To find the maximum height, we're going to use the y direction. We can use the VF squared formula because the velocity final in the y direction at the maximum height is 0. We're going to solve for d here. Next, we need to find the range. In order to do that, you need to find the time. Again, let's go to the y direction here. We can find half of the time because we know the velocity final for half the time is 0. So plugging into this formula, we can find half of the time. Then you just need to multiply by 2 in order to get the total time. Let's go ahead and put that time in the bank so we can use it to find the range. I now know the velocity initial in the x direction and the time, so I can find the range simply by multiplying the velocity and the time. That's it for level 1. I'm going to make a separate video for level 2. I hope that this was helpful.